The last day of spring quarter. Almost there. It's gonna hang on through finals. Say the same thing about a document camera. You're almost there, document camera. You just gotta hang on. Doing weird things. Injury. Well, no. Used to be friends. Right. Hmm. All right, let's get going. I imagine you might all like to look over the practice exams and stuff your instructors have posted. Fannjiang posted something that looks relatively short, in my opinion. He did, I mean, he posted something that said, and for the previous material, look back at the previous stuff. So, okay. As far as, and then Parlac posted a final from before, which seems pretty comprehensive. So we can certainly go over problems from anything, either one. I might just start going through the Parlac problems because they seem more comprehensive, but if there are specific ones from the Fannjiang or the Parlac sample exam final, whatever you want to call it, you're welcome to make a request. But if no one says anything, I'm just going to start doing problems.
I request Professor Fannjiang.
Okay. So we can start with that one, sure. They're pretty simple. One of them we might say something about. So looking at Fannjiang here for a hot minute. Yeah, these are not too terrible, but they're not that great. So let's look at this. There's a lot of improper stuff here. So let's look at this first. The integral from 1 to infinity of 1 over 1 minus x squared. If people on Zoom have requests, you're also welcome to make requests. We'll work through these. We should be able to get through them pretty quickly, I think. This is 1, 1. So here, if I was doing this problem, the first thing I would do is I would write it as the limit as a approaches. No, the first thing I would do is not that. Sorry. The first thing I would do is recognize that this is an improper integral and there are two problems. Infinity is always a problem, and in this case, 1 is also a problem. So you have to break it up as the integral from 1 to take your pick. I like the number 6. Plus the integral from 6 to infinity of 1 over 1 minus x squared. A more typical choice might be the number 2, but really anything that's between 1 and infinity is a valid choice. And then you would write these as, this first one is the limit as a approaches 1 from the right of the integral from a to 6 of 1 over 1 minus x squared, plus the integral from, plus the limit as b approaches infinity of the integral from 6 to b of 1 over 1 minus x squared. And then you have to actually integrate it. Yeah, you do. So this is a partial fractions integral. And since I have a lot of stuff going on over here, what I would generally recommend doing is do the indefinite integral off to the side. So especially if it's more complicated than just a straightforward, the antiderivative. So off to the side over here, we're going to say, well, we know it's partial fractions. So we're going to say that 1 over 1 minus x squared is equal to 1 over 1 minus x times 1 plus x. And that's going to equal a over 1 minus x plus b over 1 plus x. Multiply both sides by the common denominator to get 1 on the left, a times 1 plus x on the right, plus b times 1 minus x. Pick nice values of x. So here we're going to pick x equal to 1 and get 1 equal to a times 2 plus b times 0. So a is 1/2. Similarly, if x equals -1, you're going to get 1 still on the left equal to a times 0 plus b times 2. So b is also equal to 1/2. How lovely. And we can even do the integration. So the integral of a over 1 minus x, so 2 over 1 minus x, plus 2 over 1 plus x. Sorry, not 2. Where'd the 2 come from? It's not 2, it's 1/2. Sorry. 1/2 over 1 minus x plus 1/2 over 1 plus x. That's going to be a -1/2 natural log of the absolute value of 1 minus x plus 1/2 natural log of the absolute value of 1 plus x. And it is important when you get a natural log situation like this that you do combine them into the more compact version, especially when their coefficients are the same or opposites of each other. Yeah.
Is that a B or a 6?
That's a B. Well, there's a 6 up here. That's a B right here.
Where'd you get the 6?
I made it up. I picked any number I wanted between 1 and infinity. So let me back it up because you were here. So for this improper integral, 1 is a problem and infinity is a problem. And we know that for improper integrals, we can only deal with one problem at a time. So we broke it up into 2 integrals that each have one problem. And I picked 6 because I like the number 6. But you can really pick anything. 2 is probably the standard choice here. But I wouldn't pick 8 because that's really my favorite number, because 8 kind of looks like infinity sometimes and it can just be confusing. So don't pick 8 because it might look like infinity, but pick anything you like. So then we're going to rewrite this, and you can really do this. Oh, sorry. We were still writing this as 1/2 times the natural log of the absolute value of 1 plus x over 1 minus x. I still think 1's going to be a problem. Question.
How do you know which 1 plus x?
So I skipped a step. That's really 1/2 times, I'm going to write this one first. It's the natural log of the absolute value of 1 plus x minus the natural log of the absolute value of 1 minus x. So whichever one's being subtracted goes to the bottom. So I would point out that if it were just the piece that goes to infinity, this actually would end up converging. Because the limit of the inside part is 1 plus x over 1 minus, the limit of 1 plus x over 1 minus x is just 1. Or sorry, negative 1. Apologies. So if you're doing this, it's advantageous to try to do the part that you think might diverge first. Because if part of it diverges, you can stop and say the whole thing diverges. You don't have to look at the rest of it. So if it were me, I would specifically focus on the first part here. Say that's going to be the limit as a approaches 1 from the right. We just did the integral. The integral of 1 over 1 minus x squared is exactly 1/2 natural log of the absolute value of 1 plus x divided by 1 minus x from a to 6. Now we plug in the limits of integration. We get the limit as a approaches 1 from the right of 1/2 times the not very important natural log of 1 plus 6 over 1 minus 6. The absolute values are important here, right? It's the natural log of the absolute value of 1 plus 6, which is 7 over negative 5. And if you don't have the absolute values there, it's a problem because you can't take the natural log of a negative number. That's some number minus 1/2 times the natural log of the absolute value of 1 plus a over 1 minus a. And now we have to ask ourselves, what happens as a gets closer and closer to 1? Well, as a approaches 1, this fraction here gets closer and closer to 2 over 0, which is blowing up to some sort of infinity. And it doesn't really matter if it's positive or negative because we're taking the absolute value of it. So the absolute value of that is for sure going to positive infinity. And the natural log of something that's getting infinitely large is also getting infinitely large. So this is going to end up diverging. It's going to diverge to, I don't care what 1/2 times natural log of 7/5 is, minus 1/2 times something that's going to infinity. So this is going to negative infinity. We don't really care because they didn't ask us what it diverges to. So once you got to here, you should just say, yeah, this integral diverges. If we were asked what it diverged to, then we would have to do the work of the other piece of this and figure out whether this converges or diverges. If this other piece converges to a finite number, then the whole thing diverges to negative infinity. If this other piece diverges to negative infinity, then negative infinity plus negative infinity is negative infinity, and the whole thing diverges to negative infinity. But if we were in the unfortunate situation where this piece diverged to positive infinity, then this negative infinity plus positive infinity is an indeterminate thing. We can't say what it diverges to. We can only say that it diverges. Do we want to do this other piece? I don't want to do it. You definitely shouldn't do it on a test unless you were asked to do it. But if we wanted to see what, I'll explore that other piece just so everyone can see what happens here. If we do look at the other half of that, the limit as b approaches infinity of the integral from 6 to b of 1 over 1 minus x squared ends up being the limit as b goes to infinity of 1/2 the natural log of the absolute value of 1 plus x over 1 minus x evaluated from 6 to b. 6 might not be a great choice because my 6s sometimes start to look like b's. Pick something that's easily distinguishable if you can pick anything you want. It's not going to get mixed up as you write fast. So then limit as b goes to infinity of 1/2 natural log of 1 plus b over 1 minus b minus 1/2 natural log of 1 plus 6 over 1 minus 6. And in this case, as b goes to infinity, 1 plus b over 1 minus b goes to negative 1. Because you have a b to the 1 over a negative b to the 1, and the limit is the quotient of the leading coefficients, which is 1 over negative 1. So then you get the natural log of the absolute value of negative 1, which is just natural log of 1, which is 0. So this part would converge to negative 1/2 times the natural log of 7/5. Again, that's not important in the context of this problem because we weren't asked to deal with all the pieces. We were just asked to determine whether the whole thing diverges or converges. On the other hand, if they had asked you in the beginning, say the integral from 1 to 20, then that integral would converge because the only problem would have been 1, and we can see that it's convergent at 1 or when we approach 1. No, because what I did here was I said absolute value of 7 over -5 is just 7/5. Yes, it is. Yeah. Yeah, if you have a negative thing inside an absolute value, you can just say it's the positive thing and drop the absolute values. You're literally taking the absolute value of it and getting whatever the positive number is. Let's look at the second piece here. I mean, I should make sure I'm looking at the chat. There is something in the chat. Can we do 5 from Fannjiang? Yes, we will definitely get to 5. Oh, 5, sure. Oh yeah, 5's fine. Yeah, 5's okay, sure. I might skip 3, but we'll see. Because we already did it in class a while ago. So I'll find out we did 3 before. So I don't think I used A, but okay. So here's question 1, part 2. So the integral from 1 to infinity of, I would prefer to write this as 1 over x natural log of x dx. Infinity is a problem. Are there any other problems? 1's also a problem because the natural log of 1 is 0. So we do have to break this one up as well. Integral from 1 to 3 of 1 over x natural log of x dx plus the integral from 3 to infinity of 1 over x natural log of x dx. And then we again write this as the limit as a approaches 1 from the right of the integral from a to 3 of 1 over x natural log of x dx plus the limit as b approaches infinity of the integral from 3 to b of 1 over x natural log of x dx. Again, good to do the integration off to the side. The integral of 1 over x natural log of x. This one should be pretty straightforward. To u sub, we're going to pick u equal to the natural log of x. Our du is exactly what we hope it is. It's 1 over x dx. So this integral becomes the integral of 1 over u du. And that integral is the natural log of the absolute value of u, which is the natural log of the absolute value of the natural log of x. In this case, I would focus on the part with infinity, because we know that natural log of something that gets infinitely large is also infinitely large. So the natural log of infinity is going to grow, albeit very, very slowly. It is going to grow infinitely large. So I'm going to focus on this piece here. Say that that piece is equal to the limit as b goes to infinity. The integral of that is the natural log of the absolute value of the natural log of x from 3 to b. We plug in, we get the limit as b goes to infinity of the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 3. And then you have something that's getting infinitely large. So it's infinity minus the constant, which is infinity. So this one also diverges. How disappointing. And just for the sake of interest, I will point out that the other part also diverges. Because if you plug in 1, natural log of 1 is natural log of 0, and the natural log of 0 diverges down to negative infinity. So either piece would have diverged here. All right. Let's look at since we're already talking about improper integrals, let's go ahead and hit part 2 as well, or problem 2 as well. It's kind of gnarly. So the first part here, we're trying to find the values of p so that the integral from 1 to 2 of 1 over x natural log of x to the pth power dx converges. So, point of interest. If p is negative, for example, if p was equal to -3, you don't probably really need to write this part down, but fine if you do. You'd have the integral from 1 to 2 of 1 over x natural log of x to the negative third, which I would choose to write as the integral from 1 to 2 of the natural log of x cubed over x. Notably, that integral is proper. It's not undefined anywhere. Natural log of 1 is defined, natural log of 2 is defined, every point in between is defined, the denominator is always defined. So if p is negative, this thing converges, which is typical. And if p is 0, this thing also converges. With the same, right? Because natural log of x to the 0 is just 1. And then 1 over x from 1 to 2 is, again, just a nice, regular, definite integral that isn't problematic. So I don't know if the intention of this problem was really to consider p being negative, but the problem says find the values of p and doesn't specify that p should be positive. So we should be holistic. We should include everything. So certainly it's going to be p less than or equal to 0 and then some. So now we'll deal with p being positive, which is where we're going to end up having an improper integral. So now we're going to look at p being greater than 0. And let's just do the integral. The integral, the indefinite integral. It's pretty much the same integral as the previous problem, just a slightly different result because we have natural log of x to a power instead of just natural log of x. So that's going to be, we're going to do a u sub. U is natural log of x again. Du is 1 over x dx again. And we end up getting the integral of 1 over u to the p du, which is the integral of u to the negative p, which is either going to be u to the negative p plus 1 divided by negative p plus 1, as long as p isn't 1, or the integral of 1 over u to the first is the natural log of the opposite value of u. In fact, if we had been smarter about the first problem, the problem before, we would have looked ahead and been like, oh, if we were to break this up at 2 instead of 3, and then focus on this piece instead, and see that this diverges, then that would have told us that when p equals 1, it's going to diverge. That would have been really smart to do if we've been looking ahead. So sometimes it's good to look ahead in your test and be like, oh, can I kind of save myself some work here? Probably not super likely, but you never know. So then we're going to evaluate this improper integral. So the integral from 1 to 2 of 1 over x natural log of x to the pth power. The 1 is the problem. So we're writing as the limit as a approaches 1 from the right, because we're between 1 and 2. So we're to the right of 1 of the integral from a to 2 of 1 over x natural log of x to the pth power dx. And then we're going to end up getting, so let's look at the p not equal to 1 case. So if p is not equal to 1, let's do p equal to 1 first. It's a little easier to deal with. So if p is equal to 1, then we're going to get the limit as a approaches 1 from the right. The integral of this is the natural log of x. From a to 2, we plug in the limits of integration. So we get the natural log of the opposite value of the natural log of 2 minus the natural log of the opposite value of the natural log of a. And then as a goes to 1, the natural log of a goes to 0, and the natural log of 0 goes to negative infinity. So it diverges. It is important to have that picture of the natural log of x graph in your head so that when you think about getting closer and closer to 0, you think about the natural log of x graph going down, 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 down to negative infinity. P not equal to 1 is the more annoying case here. So if we have p not equal to 1, then we have that this limit as a approaches 1 from the right of the integral from a to 2 of 1 over x natural log of x to the p. We know that it was equal to, oh, I didn't finish this off. I apologize here. I forgot. I didn't replace, sorry, you can't quite see that. Sorry. I didn't finish this off by writing that u was equal to the natural log of x here. So I should have finished this off and said that this was equal to the natural log of x to the negative p plus 1 divided by negative p plus 1. So that's what this integral is equal to. It's equal to the natural log of x to the negative p plus 1 divided by negative p plus 1, evaluated from, oh, I don't forget the limit, James. The limit is a approaches 1 from the right, from a to 2. Goodness, okay. We do the same thing. Yeah, sure. We do the same thing. Plug in, the limit is a approaches 1 from the right of the natural log of x to the negative 2 plus 1 over negative 2 plus 1. I'm sorry that I wrote the wrong thing there. I'm not plugging in 2 for p. Or am I plugging in 2 for? Right, I'm plugging in 2 for x. Let's try again. So it's going to be the natural log of 2 to the negative p plus 1 divided by negative p plus 1 minus the natural log of a to the negative p plus 1 divided by negative p plus 1. Okay, so here's what's going to happen. Where is the natural log of a going towards if a is approaching 1? Natural log of 1 is 0. So this is going to 0. 0 to a positive power is just 0. 0 squared, 0 cubed, etc., etc., etc. 0 to a negative power is undefined. It's like 1, 0 to the negative third is like 1 divided by 0 cubed. 0 cubed is 0, 1 divided by 0 is a problem. So essentially, this is going to converge if that power is positive, which means p should be less than 1. Just add p to both sides. It's going to diverge if that power is negative. So add p to both sides. P is bigger than 1. So what I would say here is that we get convergence if p is less than 1, divergence if p is bigger than 1. And that p less than 1 does include negative values as well, because we already talked about if p was negative, how it's going to converge. Blech. And then the other p's. It's kind of a lot. So let's look at the other piece here. So I would point out the other piece we've already done a lot of the work for. The other piece is asking about the integral, the same integrand with different limits of integration. So it's integral from 2 to infinity of 1 over x natural log of x to the p power. I will point out in this case, if p is negative, you get a natural log of x on top, and the natural log of x will blow up to infinity, so it will diverge if p is negative. This is going to diverge if p is negative or equal to 0. Because if p was 0, the natural log of x to the 0 is just 1, and the integral from 2 to infinity of 1 over x we know is a divergent integral. It's your kind of standard choice of divergent. So then let's look at when p is positive. We already did the integral here, right? We know that this is going to be equal to limit b goes to infinity of the integral from 2 to b of 1 over x natural log of x to the p, but that's literally the same integrand as before, and that's going to either equal two different things, right? It's either going to be the natural log of the absolute value of natural log of x if p is equal to 1, or it's going to be the other thing we had, which was the gross natural log of x to the negative p plus 1 divided by negative p plus 1 if p is not equal to 1. So doing this case first, we're going to get the limit as b approaches infinity of the natural log of the absolute value of natural log of x from 2 to b. We're going to plug in, and we're going to see divergence here. You get the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 2. This part goes to infinity. Diverges. And if p doesn't equal -1, well, then we're going to have to break that up into two cases. So we're going to have the limit as b approaches infinity of the natural log of x to the negative p plus 1 over negative p plus 1 from 2 to b. Goodness gracious. Almost done with this problem. That's going to be the limit as b approaches infinity of the natural log of b to the negative p plus 1 over negative p plus 1. We don't really care about this next part, but we're going to write it anyway. Natural log of 2 to the negative p plus 1 over negative p plus 1. Finally, b is going to infinity. Natural log of b also goes to infinity. Infinity to a positive power grows infinitely large. Infinity to a negative power is like 1 over infinity to a positive power. It gets really, really small. So here, if the power is positive, we get divergence. So if p is less than 1 or equal to 1. And if the power is negative, then we get convergence. So that would be p being larger than 1. Kind of a lot. It's a lot of a problem for 2 problems. Yeah, question. Sure. So if negative p plus 1 is less than 0, then what you have is, let's just write it up here because I think we can fit that in. Yeah. So you have the limit as b goes to infinity of the natural log of b to the negative p plus 1 divided by negative p plus 1. I'm not going to write the other part here because that part's just some constant. But then negative p plus 1 is negative, right? So I'm going to rewrite this as the limit as b goes to infinity of 1 over, still have the negative p plus 1, and I'm going to have the natural log of b to the positive p minus 1. But p minus 1 is positive because it's the negative of a negative. And natural log is going to infinity. Infinity to a positive power is still infinitely large. And then division by an infinitely large thing gets infinitesimally small. Correct, yes. 0 is a real finite number. Any real finite number, including 0. Well, in fact, I should say this doesn't converge to 0. This converges to 0 minus the natural log of 2 to the negative p plus 1 over negative p plus 1, whatever that ends up being, which is terrible. But probably something positive. Okay, so I will point out that on this exam, we pretty much did problem 3 in class the other day where we found the arc length of one arch of a cycle. You know what, we should probably do it because there is something to see. So we'll do this one relatively quickly. I can say. So problem 3, arc length of the cycloid x equal to a times t minus sine t and y equal to a times 1 minus cosine t. Yes, of course. For parametrically defined equations, the arc length formula is going to be the integral of the square root of dx dt squared plus dy dt squared dt. In this problem, you do need to know that you get one arc of the cycloid as your parameter goes from 0 to 2 pi. Because again, the cycloid is that thing where you have like the rock stuck on the wheel and you have one full revolution of the wheel gives you one full arc of the cycloid. So our limits of integration are going to be from 0 to 2 pi. Okay. dx dt is, well, let's just write it out. So we get the integral from 0 to 2 pi, square root of dx dt is going to be a times 1 minus cosine t. We're going to square that. dy dt is going to be a times sine of t. We're going to square that. we're looking for simplification. So we have the integral from 0 to 2 pi of the square root of, I would point out here that you're going to get an a squared here and an a squared there. And you can factor out the a squared inside the square root as an a outside of the square root. And then you have 1 minus cosine quantity squared, which is 1 minus 2 cosine t plus cosine squared t. And you have a sine squared. And I know you all know that cosine squared plus sine squared is equal to what? Right. 1 plus 1 is 2. So we can rewrite this as a times the integral from 0 to 2 pi of the square root of 2 minus 2 cosine of t. There are two different ways to approach this. Both of them are terrible. I'm not gonna lie, both of them are terrible. It's a fact. Both of them are terrible. One way to approach this is to multiply by a conjugate. So I'm gonna actually factor out a 2 from the inside as well. So I'm gonna write this as a times the square root of 2 times the integral from 0 to 2 pi of the square root of 1 minus cosine of t. Then what you're going to do is you're going to multiply that 1 minus cosine of t over 1, because it is divided by 1, by its conjugate. 1 plus cosine t, 1 plus cosine t. Because what else could you do? Well, there is something else you can do, but it's probably even harder to figure out. And then we multiply it out. You get a root 2 integral from 0 to 2 pi of the square root of 1 minus cosine times 1 plus cosine is 1 minus cosine squared. And the reason we did that is because 1 minus cosine squared is equal to sine squared. In the bottom, 1 times 1 plus cosine is 1 plus cosine. Yeah. I would point out that there is some symmetry in this picture because I don't want to deal with the absolute value here. So this arc length, this arc of a cycloid kind of looks like this. Nope, you can't even, no, yeah, you can. So from 0 to pi, you get exactly kind of half of the arc length. So I'm going to do something kind of tricky and say it's equal to 2 times a root 2 times the integral from 0 to pi. The reason I'm doing this is because I don't want to have to say that the square root of sine squared is the absolute value of sine. And if I'm integrating from 0 to pi, sine is always positive in the first and second quadrant from 0 to pi. So you can say it's just going to be sine. I know that's kind of annoyingly tricky, but it's better than dealing with an absolute value. And then you make a u sub. You let u equal 1 plus cosine t. Your du is negative sine t dt. So negative du is positive sine t dt. We rewrite this as 2a root 2 integral. The sine t dt becomes a negative du. The square root of 1 plus cosine becomes the square root of u. And my new limits of integration are, well, if t is 0, 1 plus cosine of 0 is 1 plus 1, which is 2. And if t is pi, 1 plus cosine of pi is 1 plus negative 1, which is 0. And if it were me, and it is me, I would make the choice to change those limits of integration order because there's a negative sign I can get rid of while I do it. So I could totally rewrite this as 2 times a times root 2 times the integral from 0 to 2 of 1 over root u du, or I would say u to the negative 1/2 du. It is 100% valid to change the order there and lose the minus sign. Finally, we integrate. We get 2a root 2 times u to the positive 1/2 divided by 1/2, which is also like multiplying by 2. From 0 to 2, and then we plug in and we get 2 times a times root 2 times 2 times 2 to the 1/2 minus 0 to the 1/2. And then you simplify and you get 2 times 2 times root 2 times root 2, which is 2 times 2 times 2, which is 8a. Or you could do this a different way from this point here. I will just point out the beginning of that because it's awful in a different way. Yeah. You talking about this one right here? So I was trying to avoid using the absolute value. So what I said is this whole arc length here from 0 to 2 pi is equal to double the arc length from 0 to pi. Because there is symmetry there. But yeah, I'm not gonna lie, it's a little cheatery. Kim, what does the answer say? It says 8 times A. Sorry, that is an A. Yeah. Where A is essentially the radius of this circle. So the arc length here is 8 radial lengths of the circle. I will just point out that alternatively, and we did do this in class before, that if you're integrating the square root of 2 minus 2 cosine t, I'm not going to sweat the A or the limits of integration for a second here. You can write this as, well, you can use a trig identity. You can use the half angle identity, which says that sine squared of an angle is equal to 1 minus cosine of 2 times that angle divided by 2. And then what I'm going to do is I'm going to make this look like that by multiplying both sides by 4. So that 4 times sine squared of theta equals 4 times 1/2 times 1 minus cosine of 2 theta, which is exactly 4 sine squared theta equal to 2 times 1 minus cosine of 2 theta. But I want a t instead of a theta, so I'm going to say that, great, I want this 2 theta to equal t, so theta is going to equal t divided by 2. So what I actually have is 4 times sine squared of t divided by 2 is equal to 2 times 1 minus 2 times cosine of 2 times t divided by 2. And then that is exactly the same as that, and you can replace it with that. I know this does not seem more obvious in any way. I think it's less obvious to do, but it is another way of getting there. It's probably a little bit less complicated as far as the actual stuff you have to write down. So then if we did it that way, we'd have the integral of A times the integral from 0 to 2 pi of the square root of 4 times sine squared of t over 2. The nice thing about this is there really isn't an absolute value you have to worry about, because if t goes from 0 to 2 pi, t over 2 goes from 0 to pi, and sine is always positive if your angle is from 0 to pi. So you can really do this as just equal to A times the integral from 0 to 2 pi. The square root of 4 is 2. The square root of sine squared is just sine. You integrate, you get A times 2 times negative cosine of t over 2 divided by 1/2 from 0 to 2 pi. You plug in 2 times 2 times A is 4A, and then negative cosine of pi is 1 minus negative cosine of 0 is -1. And look, you get 8A again. I don't think either way is particularly good, but those are kind of your choices. I would be displeased if this occurred on your final, but I'm not the one writing your final, so I hope this problem doesn't come up on your final because I think it's kind of awful for a final. But if it did, at least you've seen how to proceed. So you can either, when you get to the 1 minus cosine, multiply by the conjugate, 1 plus cosine over 1 plus cosine, and then it's kind of a lot. Or you can see, oh, I see a 1 minus cosine, or a 2 times 1 minus cosine. And remember that 1 minus cosine pops up in the sine squared half angle formula. Those are your options. Okay. Let's look at the next two here. We have 4, which is the arc length of, yeah, okay. So we want to find the arc length of r equal to 1 minus cosine theta, where theta is between 0 and 2 pi. So the arc length formula for polar coordinates, we did talk about briefly. The length is equal to the integral from 0 to 2 pi. It's the square root of the derivative of r squared plus r squared. It's actually not too terrible a formula. I mean, considering all the other terrible formulas we've seen. So that's going to be the integral from 0 to 2 pi. The square root of, let's see, the derivative of r is positive sign. It's going to be sine theta squared or sine squared theta. And r of theta is 1 minus cosine theta squared d theta. So then we're going to get the integral from 0 to 2 pi of the square root of sine squared theta plus 1 minus 2 cosine theta plus cosine squared theta. This looks like the thing we just integrated. Which I suppose if you had just asked this question before, it's kind of terrible still because it's a hard question, but like at least you've already done the work. You've supposedly done the work already. So simplifying this, sine squared plus cosine squared is 1. And look, we exactly have the integral from 0 to 2 pi of the square root of 1 plus 1 minus 2 cosine theta. And that's going to be 8. Per the work we just did, right? That literal same integral, 2 minus 2 cosine t from 0 to 2 pi with an a in front of it, ended up being 8 times a. Get rid of the a, and you got 8. And I imagine that was probably the intent of putting it there, was that you had already actually done all the work. You just had to figure out what the right formula was to actually set up the arc length part. So yeah. But that is, predicated on you having done the previous part correctly, which is challenging. Yeah.
Right, so you said sine squared theta plus cosine squared theta is 1.
Yep. Yeah. Yeah. Okay, let's look at 4b. It's funny that you use A and B for some of them and 1 and 2 for some of them. Whatever. Doesn't really matter, I guess. So for 4b, still an arc length, but now we have something defined parametrically, not polarly. So it's x equal to t cubed, y equal to, and I skipped 3b, I'm sorry. I'll come back to 3b in a second here. Y is equal to 3t squared over 2. And t is between 0 and root 3. So same idea for arc length as before. The arc length, there's a lot of arc length questions on this practice exam. I guess this is not the whole practice, right? He said this was the stuff for just the recent stuff, and then you should look at the other things if you're in this class for the other practice. So this is not the entirety of a practice, it's just the chapter or whatever stuff. So same idea here, we're gonna do the integral from 0 to root 3, square root of dx dt squared, so 3t squared squared plus dy dt squared. Dy dt is going to be 3t. It's going to be 3t quantity squared. So we're going to get the integral from 0 to root 3 of the square root of 9t to the 4th plus 9t squared. Factoring is your friend. Inside the integral there, not the integral, inside the square root there, what can I factor out? Yeah. So we have a 9t squared times t squared plus 1. And then the square root of 9t squared is 3t. Again, no absolute value is necessary here because our t's are already always positive. That's going to be the integral from 0 to root 3 of 3t times the square root of t squared plus 1. I don't even feel like I should finish this problem. This one's super straightforward compared to the other ones. It's a u substitution. So that u equal the inside of your square root. U is t squared plus 1. Du is going to be 2t dt. So 1/2 du is going to be t dt. So here's my t dt. I'm going to replace that with a 1/2 du and get 1/2 du. I still have that 3 there, which I should have put out in the front. And then I have the square root of u. we might as well change our limits of integration. If t equals 0, u is going to equal 0 squared plus 1, which is 1. If t equals root 3, u is going to equal root 3 squared plus 1, which is 4. How nice. We get 3 halves times the integral of u to the 1/2 is u to the 3 halves divided by 3 halves. That works out pretty nice. Those cancel, and you just get 4 to the 3 halves minus 1 to the 3 halves. You should simplify this further to get a final answer of 8 minus 1, which is 7. Okay. Looking back at 3b, because I forgot there was a 3b. 3b is that same arch of a cycloid, but then finding the surface area generated by revolving one arch about the x-axis. So, very, very generally, arc length is equal to the integral of ds, where ds is either the square root of 1 plus f prime of x squared, or the square root of 1 plus g prime of y squared, or the square root of dx dt squared plus dy dt squared, or the square root of r prime of theta plus r squared plus r, right? There's like 4 different r lengths. But they all break down as just the integral of ds, where ds is the square root of whatever thing you need. And then surface area is equal to the integral of 2 pi times your radius times your ds. And your radius is equal to x if you're going around the y-axis. And your radius is y if you're going around the x-axis. So in this case, it's going to be the same terrible integral we did before, which let's look back at it real quickly. I know. So let's look back at the simplified version of it. Sure. So here's our simplified version of the previous arc length integral. The arc length was the integral from 0 to 2 pi of a times the square root of 2 minus 2 cosine t. And then to find the surface area, we would, so again, I'll point out, that's your ds right there. And this is, I should say, this is 3b, by the way. So for 3b, same curve around the x-axis. So our radius is y. And y in that problem was equal to a times 1 minus cosine t. So here, our surface area is going to be a times the integral from 0 to 2 pi of your 2 pi times your radius, a times 1 minus cosine t, times the square root of 2 minus 2 cosine t. That looks terrible. I have no idea what you're supposed to do here. Did you post solutions? You did? Curious. Okay, I'll take a look real quick. Let's see here. Fannjiang. I have ideas, but they're terrible. Let's see, he posted this in the modules. At the bottom. Nope, no solutions as of yet. Bummer. So yeah, I really am like, I'm not sure how you would. I mean, I have ideas. I just feel like they're all gonna be awful.
Because the stripe, I'm not sure.
Oh, sure, yeah. I mean, so this integral, we did the thing we did before. Guess that? No, that's still really awful. We did the other thing we did before. Not better. Yeah, I'm not sure how you would integrate that without it being extremely awful. I don't feel like I'm missing anything, right? Because it's the same ds as we had before in the problem 3a. We're multiplying by 2 times pi times the radius. The radius is y, because you're going around the x-axis. And what I'm seeing here is that this really looks like 2 pi times a squared. I'm going to factor out a 2 here and get a root 2. And then I'm left with the integral from 0 to 2 pi of 1 minus cosine t times 1 minus cosine t to the 1/2. So that's 1 minus cosine t to the 3/2 power. That might work out, actually. Yeah, okay. So I think we have to kind of do it the second way we did it, where we replaced. Yeah. So then, just like before, we said sine squared of t over 2 is equal to 1 minus cosine of t over 2. And then I'm going to multiply both sides by 2 to get 2 sine squared of t over 2 equal to 1 minus cosine of t. And then I would replace the 1 minus cosine of t with the 2 sine squared of t over 2. You get 2 pi times a squared times root 2 times the integral from 0 to 2 pi of 2 sine squared of t over 2 to the 3/2 power. Then no one should put this problem on the test. But then what you would get is 2 pi times a squared times root 2. You get 2 to the 3/2, which is the square root of 2 cubed. And then you have still the integral from 0 to 2 pi. Sine squared to the 3/2 is sine cubed. Okay, you're almost there. And then for sine cubed, you have to do the thing where you break it up as a sine squared times a sine, and then replace the sine squared with a 1 minus cosine squared. So you can do a u sub. So that's going to be 2 pi times a squared times the square root of 2 times to the 4th, which is just 4. And then you have the integral from 0 to 2 pi of sine of t over 2 times sine squared of t over 2. And then we do a u sub. You let u equal cosine of t over 2. du is negative sine of t over 2 times 1/2 times dt. So then negative 2 du is equal to sine of t over 2 dt. So then we can rewrite this as 8 pi times a squared integral. We'll change those limits in a second. Your sine of t over 2 times dt is your negative 2 du. And then the 1 minus cosine squared is going to be your 1 minus u squared. Your new limits of integration, if t is 0, that's a problem. No, it's not. If t is 0, cosine of 0 is 1. If t is 2 pi, cosine of 2 pi over 2 is cosine of pi, which is negative 1. I would again do the thing where I flip them because they're out of order and I have a negative to deal with it. So I'm going to write this as positive 16 pi a squared integral from negative 1 to 1 of 1 minus u squared. I multiplied the 2 out in front and ignored the negative. And finally, oh my goodness, 16 pi a squared. We integrate the insides, we get u minus u cubed over 3 from negative 1 to 1. We get 16 pi a squared times 1 minus 1/3 minus negative 1 plus 1/3, which ends up being 4/3 times 16 pi a squared. So we get 64 pi a squared over 3. Might be one of the worst problems I've ever done. And I've done a lot of terrible problems. So I would really, really be surprised to see a problem of that difficulty on an exam. The takeaway here should be the arc length, the surface area. And surface area, you're going to start off by doing, sorry, I lost my place here. Gone. But yeah, surface area, right? It's the integral of 2 pi times r times ds. And your job is to figure out what the appropriate R is and what the appropriate DS is. Okay, whew, that was a bit much. So let's look at number 5, because that was one that someone definitely been waiting for. I feel like I should go in order here. Let's look at number 5 now. So number 5 is find the following areas. So 5A, that's not the pen I want to use. So we want to find the area of the region enclosed by. I will say the advantage of Parlax's exam is she did post the exam with solutions. Which I suppose I could, yeah, if I remember to do it, I can post her exam on Canvas and his exam on Canvas as well. So people from the other classes can see the other things if they'd like to. It's probably good practice. Region enclosed by x equal to cosine cubed t, y equal to sine cubed t, t between 0 and pi over 2. The x-axis and the y-axis, okay. So this is some parametric curve that's doing something in the x-axis, or in the coordinate plane. I'm not going to graph it accurately, but I'll point out that if you plug in 0 for t, cosine of 0 is 1, sine of 0 is 0. So you get the point 1, 0. Then you plug in pi over 2, cosine of pi over 2 is 0, cosine of pi over 2 is 1. So you get the point 0, 1. It's not going to look like a circle, because cosine cubed plus sine cubed doesn't just equal 1. So I just know I've got something kind of funky. I don't really know what it is. It probably looks much nicer than that. But I'm looking for this area here. So I think the way we're supposed to do this is the following way. For parametric equations, we can basically say, well, x is some function of t, y is some other function of t. And we're just trying to find the area under this curve. And if we have the wherewithal or the means, it would be possible to find y equal to f of x. Well, this one, I think this one has an interesting trick to it. So I really want to find we could find this, and then we could just do the integral normally of f of x dx. That's not what we're actually going to do, but this is going to tell us how we get what we need. So f of x is just y. So I really want the integral of y dx. And then check out this trickery. X is h of t. Dx dt is h prime of t. So dx can be replaced with h prime of t dt. And y can be replaced with g of t. This is going to be equal to the integral of g of t times h prime of t dt. So basically, the parametric equation of y multiplied by the derivative of the parametric equation of x. And I think, I'm not 100% sure, but I'm pretty sure to find the area, you have to integrate in the direction that goes from left to right. And the leftmost point is when t equals pi over 2. And the rightmost point is when t is equal to 0. So I think we have to integrate from a lower limit of pi over 2 to an upper limit of 0. If it were wrong, or if it were wrong the other way, and if I did it the wrong way and I got a negative answer, I would just go back and literally cross them out and change them and get a positive answer. That's actually what I would do. But I'm pretty sure you want to go from left to right. So let's see what we get here. We have the integral from pi over 2 to 0. G of t is just my sine, whatever y was equal to. So I keep feeling I'm off screen here. So g of t is just sine cubed. Oh my God, you gotta be kidding me. Sorry, I'm just seeing what I think this is going to be. And if it is what I think it's going to be also terrible. And h prime of t, the derivative of cosine cubed is 3 times cosine squared times the derivative of cosine, which is negative sine. And I kind of want to swear because This is absolutely, maybe even worse than the ones we just did. So here's what we have. We have -3 times the integral from pi over 2 to 0 of sine cubed times sine, which is sine to the 4th, times cosine squared. And this problem, assuming we've done things correctly, when you have only even powers of sine and cosine, you have to use those half angle trig identities to rewrite it. So this is really, really gross because it's going to be, here's what you've got. You've got -3 times the integral from pi over 2 to 0 of sine squared of t times sine squared of t times cosine squared of t. And our only option here is to replace each sine squared with 1 minus cosine of 2t over 2. And cosine squared with 1 plus cosine of 2t over 2. So I would do a couple things. I would bring out the 1/8. I would drop the negative and change the order of integration. It's going to be a positive 3/8 integral from 0 to pi over 2. And then I would multiply together first the 1 minus cosine times 1 plus cosine, because at least that's a difference of square. It'll multiply out so that the middle terms cancel. So you're going to have this 1 minus cosine of 2t multiplied by this, which is going to be 1 minus cosine squared of 2t. Who wrote this? Practice problems. I can't. I'm just kind of flabbergasted that they're so difficult. And then multiplying this out further, you get 1 minus cosine squared of 2t. And then minus cosine times 1 is minus cosine of 2t. I probably could have done it in the other order. And finally, minus and minus is plus cosine cubed of 2t. Okay, let's break this up into 4 integrals because there's 4 different. Let's break it into 3 integrals. So we're going to write this as 3/8. It's an 8 times the integral from 0 to pi over 2 of the pieces we know how to integrate. The pieces we know how to integrate without any further work are 1 and cosine of 2t. Both of those have relatively straightforward integrals. And then we have minus the integral from 0 to pi over 2 of cosine squared of 2t, which is again going to require that same identity that we just used 3 times. Finally, plus the integral from 0 to pi over 2 of cosine cubed, which is going to require rewriting it as cosine times cosine squared. So then let's see what we've got. We've got 3/8 times the integral. So this integral here is going to be t minus sine of 2t over 2, evaluated from 0 to pi over 2, minus 3/8 times, we're going to replace cosine squared of 2t with 1 plus cosine of 2 times 2t over 2. Finally, over here, this is your 1 minus sine squared of 2t. So we're going to let u equal sine of 2t. du is going to be 2 cosine of 2t dt. So we're going to get a 1/2 du equal to cosine of 2t dt. So we're going to get the integral of, sorry, my brain is ending. We're going to get a 1/2 times du, and then a 1 minus u squared. Yeah. And the new limits of integration are going to be from, if t is 0, sine, oh my goodness, that might be beautiful. Let's hope that I haven't made a mistake here, but I think what's going to happen here is if t is 0, sine of 0 is 0. And if t is pi over 2, sine of pi is also 0. That feels wrong, but I guess it might not be. If your limits of integration end up being saved after a u sub, that part should just be 0. That seems a little weird. Let's look at Desmos real quick. I'm curious if I'm making a mistake or if we're just, if finally luck has turned our way briefly here. So if we look at the graph of cosine cubed of 2t. Sorry, I know you can't see this. I'm just writing it here real quick. Why can't you graph that for me? What's your problem? Fine, let me try this again. I don't understand. It doesn't want to do it. Let's try it again. So we look at y equal to cosine of 2x, and then we cube it. I guess I can do it that way. I was doing it kind of weirdly before. Sorry, my cursor's right in the way there. Okay, I believe it. Right, that looks like if you go from 0 to pi over 2, then it looks like those areas cancel each other out. From there, let me zoom in. Right, there's pi over 2. Yeah, look, this area here and that area there totally cancel each other out. We're so lucky. I hope you can hear the sarcasm in my voice because I am beat. I mean, we are lucky that that part goes away, but the rest of the thing is still really awesome. But we're almost done. So we've got 3/8 times pi over 2 minus sine of 2 times pi over 2 is 0. Minus 0 minus sine of 0 is 0. Minus, I'm going to bring out the 1/2 and get a 3/16. And then we're going to integrate 1 plus cosine of 4t to get t plus sine of 4t divided by 4 from 0 to pi over 2. And we're going to get 3/8 times pi over 2, which is 3 pi over 16 minus 3/16 times pi over 2 plus sine of 4 times pi over 2 is sine of 2 pi, which is 0 minus 0 plus 0. So let's say we end up getting 3 pi over 16 minus 3 pi over 32, which is 6 pi over 32 minus 3 pi over 32, which is 3 pi over 32. I'm sorry, but this problem was assigned to you. Let's see what's in the chat here. Yeah, me too, Caitlin. She said I'm cooked. I'm like, yes, I agree. Okay, so let's look at the very last problem here, which hopefully I can't imagine. I thought the other one was terrible, didn't it? Yeah, so even powers of cosine and sine, usually on an exam, you would be limited to maybe like a cosine squared times sine squared, or a cosine to the 4th, or a sine to the 4th. Having powers that add up to 6 like that, where it's a sine squared times a sine squared times a cosine squared, is just unreasonable. Well, let's look at this last one here. So the region bounded by the curves, this one's much, much nicer. Maybe I was missing something about the previous one. I don't think so, but you never know. So this one is bounded by r equal to 2 sine theta. Theta equals pi over 4. Theta equals pi over 2. We don't need to graph this, but I will graph it after we set it up. So for area using polar coordinates, it's going to be the integral from your lower bound for theta. So theta 1 equal to pi over 4 to theta 2 equals pi over 2. 1/2 times your r as a function of theta squared d theta. Which is not, it's not too terrible, but yeah. I just feel like we're hitting all the highlights of terribleness here. So we're going to get 1/2 times our 2 sine theta quantity squared d theta, which ends up being the integral from pi over 4 to pi over 2. You get 1/2 times 4, which is 2, sine squared theta. Well, hopefully by the end of today, you'll have fully embraced and remembered what sine squared and cosine squared can be rewritten as. So this is going to be 2 times the integral from pi over 4 to pi over 2 of sine squared is 1 minus cosine of 2 times theta, 2. The 2's cancel. You get the integral from pi over 4 to pi over 2, 1 minus cosine of 2 theta. We integrate, we get theta minus sine of 2 theta divided by 2 from pi over 4 to pi over 2. We plug in, we get pi over 2 minus sine of pi, which is 0, minus, we plug in pi over 4, we get pi over 4, minus sine of 2 times pi over 4, which is 1. 2. That's equal to 1. So I end up getting pi over 2 minus pi over 4 plus 1. And you could simplify this as 1 plus pi over 4. Just to point out graphically what this looks like. So r equals 2 sine theta is a circle centered on the y-axis with a radius of 1. So if you plug in theta equal to 0, you get r equal to 0. Not very exciting. If you plug in theta equal to pi over 2, you get r equal to 2 times 1. So there's the endpoints of a diameter of your circle, and your circle is like that. And then what we're essentially saying is we're starting at an angle of pi over 4, and we're ending at an angle of pi over 2. So we're looking for all this area in here. That's the idea. That's what we found. Interesting. Not at all necessary to draw that picture, but just so you can see. Okay, so good times. So that's kind of all the stuff we've done recently. I'll remind you all, there are other things that you also should be thinking about for this final that you have to take. All the methods of integration are in play. So I would just kind of remind everybody very generally, if you're trying to integrate something, you should look for a U sub first. Just do a quick check to see, can I do a U sub? But then the other methods you should keep in mind are certainly integration by parts, partial fractions. Someone will probably hit you with a trig substitution. Probably is maybe too strong. Maybe hit you with a trig substitution. If you have something like the integral of x squared plus 1 over x minus 2, you can do polynomial division first, which I think is worthwhile. There was something else that was in my mind. Oh, what am I missing? As far as methods go, try for something I'm missing. I guess there's right, yeah, U sub with the back sub. Or U sub with a then solving for x, with solving for x as a function of u, and then finding dx equal to f prime of u times du. That's also a thing we've done. Those are the methods that come to mind as far as I can think of. There's some special integrals, like some repeated integration by parts, where you have to then add the thing over to the other side at the end of the process. Like, for example, e to the x times cosine of x. That's one of those integration by parts problem where you have to do IVP twice, then you end up with the same integral showing up again, and then you add it over to the other side, and you get twice this integral equal to an answer, and then you divide both sides by 2. That's probably not going to show up, but who knows? So with methods of integration, Why is my brain not braining here? The other thing, let's look at the syllabus really quick. Just want to make sure. So that. I want to make sure I'm not forgetting anything important here. I guess there's the definition of the integral stuff, but that seems like something I wouldn't ask on the test. Sure. Fundamental theorem of calculus. So specifically, not the second part where you're like just how that's how you do definite integrals, but specifically the first part where the derivative of the integral from a to x of your f of t dt is equal to f of x. That seems certainly plausible. Oh, and then the application stuff. So we have volumes, area, surface area, arc length. And I guess for volumes, you have shell method and disk and washer method. Yeah, I feel like I think that's a pretty good list of things to be aware of. Again, not listing out the stuff we just spent all class talking about, all the polar parametric stuff. Yeah.
Oh, I have a good resource that is good for like sample problems. It's Paul's online.
Paul's online math. So just so everyone's aware, Paul's online math notes. Good source of sample problems. I'll go check that out and post it. And I'll try my best to remember to also share each class's practice stuff on our Canvas. So that if you want to look at Parlax's final with the solutions, you certainly can. I can do that. I just have to remember to do it. As far as next week, so your finals are what day?
That's Tuesday.
Tuesday, okay. Both Tuesday. So Wednesday, okay. All right. So I have office hours. So all the office hours starting tomorrow are in drop-in. So if you're looking, mostly it's gonna be me and Grant. You also see Sarah and or Jen down there. I'll be there tomorrow from 10 to 11. Other people will be there other hours. And then next week I'll be down there 10 to noon, 1 to 3. And other people will be there too. So if you're looking for help, I'll get some questions answered. That's where you can find me. And I will post that on campuses too. On Canvas, post office hours as well. I'm writing myself notes here. Okay, I think that's it. Best of luck on your finals. You all can do this. That's all I got. You can do this. I know you can do it.
It's like a rare representation. It's gonna be
I don't know. I mean, yeah.
like the possibility were like locked out. Like Aggie reduced exams, they were never that bad.
Yeah.
But that one was.
Yeah, I don't know. Like
That was Fannjiang.
yeah, that was Fannjiang. It makes me wonder.